So I named this talk From Scale to Scaling, and after hearing the morning keynote speakers, it could also be kind of from biology and cities to landscapes, so shifting our science goals into how we can measure the unmeasurable. And we know that we have tons of different definitions for scale, and the one that I kind of chose here because it fits for my focus in remote sensing is that we change the size while maintaining the same proportion. So when we have pixels and they're square, we change the size, we change the resolution, but we kind of keep the same proportions. And we know that this affects our analysis. So a recent study that we've been working on, we are trying to model chimpanzee habitat suitability in Liberia over there. So that's the little map up in the corner. And we had chimpanzee occurrence points, and then we had a whole bunch of indicator variables. We got these from climate databases, from land cover databases, from all sorts of places. They come in at all different scales. And we didn't know what scale to choose. We don't know what scale the process is happening. We don't know what our modeling scale should be. So we followed Jingle's advice and we did multi-scale analysis, hoping that something would kind of fall out of this, that some sort of domain of scale would present itself, something would emerge here that would give us a good indication of kind of where these variables start to stabilize. And so what we got instead was this kind of hot mess of shifting ranks of our indicator variables. The only one that stayed in the same rank across all of our different scales was the top one there, which was basically the amount of forest within a kilometer of where we had a chimpanzee sighting. And so we know these issues are present in geography and in landscape ecology in our world. We have these sort of issues when we're doing basically analyses at different scales. So that's our scale issue. But what I want to talk about more today is kind of this idea of scaling. So scaling is a way of measuring the unmeasurable. And what do I mean by this? We've seen this graph here today in, I think it was Mike's presentation, of evolutionary allometric scaling. So this is body mass of animals on the x-axis and their metabolic rate on the y-axis. And what science has found is that there's a very clear allometric scaling relationship between these two things. So if you tell me an animal's body mass, even if it's not one of these that's listed up here, I can probably tell you pretty closely what its metabolic rate is, simply because we know that this relationship exists. So why do we care? Well, if we look at our science goals here, we have kind of four general categories of why we do science. We want to describe things. We want to explain why things are happening, and in geography, we want to understand why things are happening in particular places. Moving around, we can kind of take that into the prediction realm. So can we predict what's happening at a different time or in a different place? And then lastly, we want to intervene. We want to create interventions that we can take and have solutions to our problems. If we kind of graft onto these Pasteur's quadrant of our relevance for basic understanding and our relevance for immediate application, in the geography realm, we tend to hang out over there. We like to describe things. We like to explain why they're happening. We like to build models to do this. And when we're working in that world, scale is really important. We have to understand basically all the talks here today, like how do we choose that scale and how are we going to describe or explain something unless we know what scale of processes and patterns are happening. And what I'm trying to kind of put forth here is that we need to start moving over here into the prediction and the intervention. And the reason we need to do that is because the world is we're not doing well, right? We're not in a good place. And if we don't start predicting what things are going to be like in the future, we can't make interventions today that prevent that situation from happening. And in order to get ourselves over here into this area, we need to shift into scaling. So how can we translate what we're finding out on the one side into solutions that we can use to predict or translate out our findings? So how do we do this? How do we do scaling, I have here? Basically, we have to start simply by building that relationship between two traits, X and Y, body size and metabolic scaling. I pulled up this figure that came from Jingle's 2004 paper on scaling of landscape metrics, because it shows a really nice example here of how this has been done in a non-biology and non-cities context. So we've done this type of scaling a lot in those two fields, but we haven't really taken it into the landscape realm or any really of our other geography phenomena. So we have here scale on the X, grain size here, but extent also works, and some sort of landscape shape index or metric or patch density, whatever. And you can see here we get really consistent, regular scaling relationships happening here. So what we've been trying to do in some of our more recent work is build on this simple logic. Where do we have these really consistent, robust scaling relationships presenting themselves to us? And can we use those relationships to extend beyond the known values to predict what's going to happen? Now that could be in the future, so temporally. It could be in another extent, so scaling extent, but it could also be scaling by grain size. So can we predict what we would find at a finer grain size than the data that we have collected? This is really important when we're working with our climate data, which are captured at pretty big spatial scales, to land cover, which are captured at 30 to 500 meter scales, but we really see heterogeneity happening at the 1 meter, the 1 centimeter scale. So can we kind of scale amongst that? And real quickly, what we're doing is basically looking at, you can see over, leave here. See over here, we start to build those scaling relationships based on the resolutions of data that we do have. And we find that there are certain landscape metrics that follow very consistent scaling relationships, and they're represented by power laws. So we know, based on Jingle's talk, that power laws aren't the end-all be-all, but they are really good for predicting things. So if we can extract from that relationship that scaling exponent that tells us the shape of that curve, and we can see how well that shaped curve is able to predict something at a finer resolution. We can start to work backwards and see if we are able to predict things and where we can predict things with good accuracy. We'll skip that. Okay, so to end here, my central point is that we want to consider kind of moving beyond simply describing and explaining where we have we know we have issues with scale, into the realm where we're predicting and intervening, and that one way that we might want to talk about doing this is through our scaling functions. And I think that's it for me. Yeah.
So thank you very much, Amy. Any one question for Amy before we open up for discussion? Yes.
Yeah, I just wondered, because there's a distinction, the way you approach classification, pixel-based or object-based, and I just wondered if you could speak to that with regard to scale.
Yeah, that's a great point. So with object-based classifications, we're usually working in areas where we already have high-resolution data, and so we're doing that to kind of eliminate some of the heterogeneity in our classification that we would get if we use a pixel-based classifier. So in terms of that, you might argue that in situations where we can do object-based, we are less in need of methods to downscale that data because we already have it. I haven't looked at those methods in particular with object-based classifications, just pixel-based, but it would be interesting to kind of see how they hold.